Hello everyone, welcome to watch this video. I am Yijun Chen. Today I'm going to talk about our work. I will introduce this work from about 4 parts. Designing garments that adapting to the shape of the body is an age-old problem in the fashion industry. In the traditional flowcharts, designing real or virtual garments is a complex and time-consuming process with iterative steps. Firstly, experienced designers carry out design ideas based on the shape of a person, and then draw a sketch of the garment. Then the pattern makers make the garment patterns and sews them into a whole garment. This process can be summarized into 2 steps: the 2D sketches for the initial design, and the 3D garment construction according to the body shape. Mapping the 2D garment sketches design to a 3D body requires a good understanding of the 3D space of the human body to adapt to the shape, and it is not an intuitive process. The design cycle of the garment is long and labor-intensive. Tuanfeng Wang presents a data-driven approach wherein the user directly indicates design fold patterns simply by sketching, while the system estimates corresponding garment and body shape parameter at interactive rates. Tiwari proposed SizeNet, which allows to estimate and visualize the dressing effects of a garment in various sizes. Gangdokdu proposed GuardNet to fit a 3D garment template to a 3D body. This is the framework of our method. Our garment generation network is an end-to-end architecture. The proposed network mainly consists of 3 modules: the sketch encoder that encodes sketch feature extracted from a sketch by Dataset, the human body shape encoder encoding human body shape parameters, and the mesh decoder based on a fully convolutional mesh decoder that decodes Latin code to reconstruct garments. To extract features from the input sketch image, we utilize the Dataset to generate a sketch descriptor. Then the sketch encoder takes the sketch descriptor as its input and generates the Latin code. The sketch encoder consists of Dataset, 10 fully connected layers, 2 convolutional layers, and 2 pooling layers. The body shape encoder consists of 2 one-dimensional transpose convolution and corresponding batch normalization and activations. Adding up to Latin code obtained by sketch encoder and shape encoder, we attempt a new Latin code with the size of 22. By multiple downsampling, we can obtain multiple connectivities with different topologies and numbers of vertices. And the size of Latin code is the result of the last layer of downsampling. After downsampling, we attempt yi with the variance coefficients aij and the global basic bk. We can compute the value of yi so that we can construct the convolutional layers. With variance density coefficients rho ij prime, we can compute the yi so that we can construct the pooling layers and residual layers. This is the structure of the convolutional mesh decoder. It mainly consists of 8 transposed convolutional blocks and 4 unresidual blocks. The Latin code is decoded to vertices data of the 3D gamma mesh by 8 transposed convolutional blocks and 4 unresidual blocks. We constructed a dataset with 3,730 sets of data. Figure shows an example in our dataset. Each set of data contains a 3D gamma mesh, a corresponding flattened mesh, a sketch image, a 3D male body mesh, and its body shape parameters. This is the result of 3D gammas generated for the text dataset. The red color indicates a large error, while the blue color indicates a minor error. Obviously, the errors mainly appear in the hem and sleeve parts of the garment. Although there are some errors, the generated garments are close to ground truth garments from the perspective of the shape and detail. Compared with the result of using piece A, ours has a better effect. Here, we show 4 examples of the same 2D garment with different human body shapes. The result shows that the same garment can be well adapted to different human body shapes. We also compare other clothing modeling methods. We have adopted the same measurement standards as the original paper, and our result is better. We implement a user interface based on the network, which allows the user to edit the sketch or body, and 3D draped garment is updated at iterative rates. The 2D sketch can be imported from an image file and added on the painting board. Different body shapes can be specified by adding the parameters. With different body shapes and sketches, the 3D garments fitting the body is updated in real time at interactive rates. Thank you for your watching.